And welcome to part 2 of lecture 16 from April 3rd. That would be a Friday at the beginning of April here in the 2020 spring semester of madness. So today, folks, we have hit the big time. We get to start talking about normal random variables. These are the main attraction. This is the headline and act. These are the random variables that are going to lead us into statistics. So the normal, together with the theorem that we'll be studying shortly called the central limit theorem, form the core of a huge swath of statistical techniques. And it will be our focus for the remainder of the course. So the normal random variable, we will begin as we always do with the definition that is comprised of the sample space and the distribution for this function, the probability distribution, which will be in the form of the probability density function here. First, I guess I should note that we do have tilde notation for normals. It's just a capital N, and the parameters here are mu and sigma squared. You might notice that those are the Greek letters we've been using to refer to mean and variance of random variables generally, and that is no mistake. We will see shortly here that these are, in fact, the mean and the variance of this normal, respectively. So, as for the formal definition, the sample space for a normal is the whole real line. Any real number is possible as the actual observed value for a normal random variable. The probability density function is this wily beast. So there's a lot going on here. We've got a coefficient 1 over the square root of 2 pi sigma squared, and then e raised to this whole expression, which is the opposite of quantity x minus mu squared divided by 2 sigma squared. So that is a fair amount of intimidating, complicated mathematical expression, but we'll talk more about this shortly. When you have such a random variable with this sample space in a PDF of this form, you say x is a normal or a Gaussian random variable, or you can say that x has a normal or x has a Gaussian distribution. The Gaussian here is capitalized. It's for Gauss, Carl Friedrich Gauss, one of the greatest mathematicians to ever live, and one of the first people to recognize the importance of expressions of this type. We call them normal random variables because they show up everywhere. So it is, we'll say this in a moment, but the PDF here, backing back up for just a second, the PDF for the normal is the famous bell curve that shows up all over the place. So when you talk about teachers expecting to see a bell curve for grade distributions, or astronomers talking about a bell curve that describes the age distribution of stars in a galaxy, just all over the place these bell curves show up so frequently that scientists began to say, like, oh, this is a normal phenomenon because it has that familiar shape. So the normal random variable shows up so often that it began to be referred to as normal. And in modern era, the nomenclature has shifted away from Gaussian into the use of the word normal more often, which is fine. Carl Gauss has enough associated with him. He doesn't need this also. But as we mentioned a moment ago, the PDF here looks crazy, and it is crazy, and in fact it's bad. But we're not going to end up integrating it explicitly. So backing up once more, if you recall, the function of any probability density function, I should say rather the purpose of any probability density function, is that you can integrate it in order to calculate probabilities associated with that random variable. So generally, if I give you the PDF, you should anticipate that you're going to have to integrate the PDF in order to find likelihoods associated with that random variable. But you're not going to have to. So we'll see shortly here that it's not even possible to integrate this beast for most contexts. And we will work around it. So the PDF looks scary because it is scary. But fear not, for it will not be able to bite us in this course. So as always, once we have introduced the basic definition for a random variable, we would like to also give a theorem which will state the mean and the variance for that random variable. And as I mentioned a moment ago, the mean for such a normal with parameters mu and sigma, the mean is just mu and the variance is just sigma. So to rehash something that's been discussed, the parameters associated with normal random variables can play different roles. And it's a bit unusual for the parameters to just be the mean and the variance straight away, for those to be given explicitly in the formulation of the random variable. It's not without precedence, so the Bernoulli random variable, its parameter was the mean associated with that random variable, though the variance was an expression that you could calculate in terms of the mean, namely p times 1 minus p. So it is not without some established standing that the parameters associated with a random variable of some type could be mean and variance. And in fact here for a normal you are just given the mean and the variance straight away as the two parameters. What this comes from, this is a very rough sketch of the proof. When you're calculating the mean of this random variable, you would be integrating x times the density function associated with this random variable. That's our definition of mean. It's always the values x weighted by the density function associated, and you integrate across the whole real line. If you strip away all the craziness in here, the core of this function is e to the negative of x squared. Mu is a constant, 2 is obviously a constant, sigma squared, 2 pi sigma squared under the root, that's all a constant. If you strip those constants away, the basic functional form of this expression is e to the negative x squared. So if I take x and I multiply it by the density function, I'm effectively looking at a term, an integrand of this type. And u substitution is an appropriate method to use for integrands of this type. The whole actual derivation of the mean is more complicated, and we are not going to do it explicitly, but it comes down basically to this. You have to be very careful with the types of u substitutions you make and what types of new constants are introduced or packaged together into new variables that are defined. It's not too bad. I'd be happy to show folks in office hours if you like, but it's not worth doing in lecture. You just have to know that the mean of this normal is mu and the variance of this normal is sigma squared. So again, as we mentioned earlier, the PDF of the normal is the world famous bell curve, the bell curve of great renown. And again, a simplified version of the PDF looks like this, with all the constants stripped away. It has this simpler form. And so the idea is that you're kind of seeing the tail associated with the exponential going off in both directions here. So whether x is positive or negative, we square it, and it's always positive. And then we hit that square value with a negative to ensure that the exponential always sees negative input. So whether you move off in the right direction with positive x or you move off in the left direction with negative x, the exponential is acting like it acts on its normal tail. If you remember the curve of the exponential, it goes up to the right and it drops down and it decays off quickly as a tail down to the left. Well, we're seeing that tail in both directions now by ensuring that the exponential only sees negative input. The shape is a little bit different. It's actually much smoother here than it would be if we just use absolute values because of the square. So you get more of this kind of like convexity change, and it comes up into the hump and then back down into the tails. So it's not exactly just two tails, two tails from exponentials stuck together. Instead, it's like that with also things having been smoothed over a bit. And in fact, it also decays a bit quicker than the exponential tail, which is remarkable because the exponential tail decays famously quickly. So these two parameters, mu and sigma squared, they determine the shape of the curve. What we've drawn here is sort of the standard reference curve. We're going to call this the classic bell curve, or the classic bell curve profile, but there are variations on this theme. Mu is going to shift this curve left and right and determine where the peak of the curve occurs. So I've drawn this one here with peak at 0, which is going to be relevant when we start talking about something called the standard normal. But I can have it peak at points off to the right here by making the mean value positive, or I can make it peak at points off to the left by making the mean value negative. And sigma squared is going to determine not just that translation left to right, but a change in the shape of the curve itself. So if we have a small value for sigma squared, when sigma squared is small, so it's a low variance random variable, it's going to make our bell curve taller and sharper. And when sigma squared is large, so for a large variance normal random variable, it is going to make our curve lower and wider. So it's going to depress the peak, and it's going to consequently push the tails up higher and add more probabilistic mass down the tails. And we'll draw some pictures right now. So here's a picture of what a bell curve might look like with sigma squared small. We're ignoring mu for the moment. I've just taken an arbitrary mean value where the peak occurs. The focus at this point is on how the shape of the bell curve changes for different values of sigma squared. So if sigma squared is small, then it is a low variance random variable, meaning the curve stays very close to the horizontal axis until you get very close to mu, and then it shoots up very high, and then shoots back down very quickly, and then it stays close to the horizontal axis again. My pictures are not great. Imagine that it's symmetric. These bell curves are all perfectly symmetric. I don't mean for it to be wonky on one side or the other. So imagine symmetry. The idea here is that for it to be low variance, that means that you do not expect to see values that are very far from the mean. The only values that are likely for this random variable are the values that are very close to the mean. So most of the probabilistic mass is concentrated near the mean, and you have a large area under the curve near the mean, meaning you're very likely to see values near the mean, whereas you have a very small area under the curve associated with intervals that are far away from the mean value mu, meaning you're very unlikely to see those. It's a small variance random variable, so values far from the mean can't be terribly likely. You do not expect to see much difference between the observed values and the mean. So values near the mean are very likely, values far from the mean are very unlikely. Again, that's low variance. When my buddy Miles plays darts, it's very likely that every dart that he throws is near the bullseye. It is very unlikely that any dart that he throws is far from the bullseye. So these tall, narrow bell curves are going to be associated with normal random variables that are low variance, where it is not expected to see values that differ by much from the mean. And that's why we see them being tall and skinny, because all of the probabilistic mass is concentrated very close to the mean. We can contrast that with the case when sigma squared is large. Here the peak has been pushed down considerably, and all that added mass has been pushed out into the tails. So the values near the mean are still the most likely of any, but they're less likely than they were for the corresponding values when sigma squared was small. We still do have a peak near the mean, but that peak is not nearly as high. So the area here near the mean is less large than it was here for sigma squared small. And the likelihood of seeing values in this interval, which is far from the mean, is more likely. The area is less small. It's still smaller than this, but it is larger relative to that central region compared to the same situation in the picture above. So for sigma squared to be large, that means it's a high variance random variable. That means it has become more likely that we will see values far away from the mean. And since there's always only a total probabilistic mass of 1, increasing the likelihood of these values far from the mean comes at the cost of decreasing the likelihood of seeing values near the mean. So for sigma squared large, a large variance normal random variable, values near mu have become less likely than they were when sigma squared was small, and values far from mu have become more likely. So let's do an example here. Let's sketch some density functions for some different normal random variables. So sketch these three density functions for these three different normals. We've got a normal with mean at -2 and variance 1. We've got a normal with mean at -2 and variance of 4. And then we've got a normal with mean at 2 and variance of 1. So these first two share the same mean, whereas the first and the third share the same variance but have different means. So let's try to sketch these. And again, I am not an artist. I apologize. I'm doing my best here, but I will ask you to use your imagination for some of these pictures. So for the first one, a mean at -2 means the peak occurs at -2. Here's the point -2 in the horizontal axis. This is in some sense the most likely value for this random variable. It's the expected value, the mean. And it has variance 1. Variance 1 always gives us the classic bell curve profile, as we're going to talk more about next lecture. But this looks like a fairly typical bell curve here, centered at -2, and having the classic profile dictated by sigma squared equals to 1. So neither too tall and sharp, nor too low and wide. For x sub 2, we have the same mean, so I've got another bell curve drawn in here peaking at the same place, but it is higher variance. And that means that the peak is going to be depressed, and the tails are going to move up in a corresponding fashion. So for this random variable, you're less likely to see values near the mean than you were before, but you become more likely to see values far away from the mean. That's characteristic of a high variance random variable. And finally, x sub 3 has the same sigma squared as x sub 1, so it's going to have that same classic bell curve profile, but this one is centered at 2. So what's meant to be indicated in this picture is that I've taken this curve for f sub x sub 1 and I've just shifted it over 4 units. So now its peak occurs at 2, but it should have exactly the same profile, exactly the same shape. Questions are welcome throughout this. We are going to be using these bell curve shapes a great deal. We're going to be thinking about probabilities as areas under these curves, just as I've sketched here in a few places. So definitely, if you have questions about the foundational material, please email me, drop into office hours, or schedule a one-on-one appointment so we can talk more about this stuff. So let's have you folks think about one of these. So I'm going to give you another 3 random variables, normal random variables, with different parameters, and I'm going to ask you to sketch their density functions, their density curves. So it'll be very much analogous to what we just did. These 3 actually all have the same mean 0, but I'm changing the variance. We've got a 0, 1, a 0, 1/2, and a 0, 2 normal random variable here. And I would like for you to sketch the density curves. So feel free to look back at your examples, look stuff up on the internet, talk to folks if you like, and unpause this when you're ready to see a solution. Alright, so let's have a look. And again, this is not my finest work, especially f sub x sub 2 should probably be narrower than it is. It peaks taller, and it's supposed to be doing that, but I feel like it doesn't look much like I think normal density curves look like. So tell the department to hire an artist if you want better pictures here. But f sub x sub 1, they're all going to be centered at 0 because they all have mean 0. The first random variable here has that classic bell curve profile, neither too tall and narrow nor too wide and low. X sub 2 was the normal that had variance 1/2, so smaller than x sub 1. And that's why we see it peaking higher and then also dropping off more quickly as we move away from the mean value of 0. So these bottom curves over here is the curve associated with x sub 2, whereas it's the top line in the middle that's associated with x sub 2. And we can contrast both of those with the case of f sub x sub 3, which was the high variance random variable among these 3. And so it peaks lowest. It is the one that concentrates its mass least effectively near the mean, and instead has more of its mass distributed to values that are further away from the mean. So it's the top curve out here, and it's the bottom curve in this inside interval. So these are what these 3 look like. These are what the density functions for these 3 normal random variables look like. And in fact, the first one that we studied here, the one that has the normal 0, 1 distribution, we're going to come to call this the standard normal random variable. We'll talk more about this next time, but this is going to be the central pivot point for our consideration of normal random variables. We'll see next time that any normal random variable can be transformed into a standard normal random variable. So questions about any normal random variable can be answered in terms of an equivalent question about a standard normal random variable. And I believe that is it for the evening. So I thank you, folks. I will see you again shortly. Have a good rest of your day.